Long story short, I'm building a game engine in Blender using geometry nodes, which is still very much an ongoing project. I'm about 6 months into development so far, and I made this series to share the magic of Blender, math, and video games all coming together into the biggest Blender project I've ever done. If you haven't seen the first episode of this series, go watch that first, then come back to this video. When we left off, we had a very simple player for our game that had some basic but important capabilities. We can move around in 3D space with our first-person player controller, but that's about it. No gravity, no collision, and right now we don't even have any frame of reference to give us an idea of where and how we're moving. In this episode, we'll start to give our player controller some of those essential capabilities. But before we do any of that, let's add some flair to our environment. We can add some lighting quickly with an HDRI, which is a 360-degree image that has lighting and visual information built in. It's very fast and simple, and is my preferred way of doing lighting when it doesn't need to be super fine-tuned. For the meshes in our world, a simple checker texture will do nicely, since it lets us easily see our movement and rotation relative to the environment. Keep in mind that for now, this environment is just a functional placeholder that we can fill in later. So now that we've got a more interesting space to work in, let's get back to our player. We can start by expanding the capabilities that we have. Right now, we can only move on one axis relative to our player, forward and backwards. Most first-person games allow players to strafe, meaning that they move side to side relative to the camera without rotating. Since our forward and backward movement is along the player's relative y-axis, we'll use the x-axis to strafe. We can just copy the process we used to handle the y-axis movement, but just plug in the x-axis. And like before, we rotate our vector as we look around so that the axis is following our player's direction. We then use that rotated vector to scale along by an amount that the user controls by taking an additional user input. To calculate our final movement vector, we add the x and y movement vectors together, and now our player can move in any direction on the floor plane. We'll take a closer look at adding vectors a bit later. Right now we have control over our movement speed by sliding the input value up and down, which, while cool, isn't the easiest or most practical way to control speed. To make this more in line with the standard gaming movement we're all used to, we'll limit our base movement, then easily add running by creating a switch that multiplies the input speed when it's turned on. Another standard first-person feature that we're all used to is looking up and down. So let's go ahead and add this as well. We don't want looking up and down to change the direction we're moving, like looking side to side does, so we can take another user input for this rotation, and then only plug it into our camera. We do need to isolate the input to the axis that we want to look up and down on, which in this case is the X. It's already getting a bit cumbersome to control all of these character inputs with the node panel, but right now we're just building the functionality. In a future episode coming soon, we can add a script to capture keyboard and mouse input and then use those to interface with the node inputs. And that'll make things a lot easier and more in line with what we expect out of a game. What goes up must come down, and while not every game necessarily needs gravity, since we have a 3D engine where we'll want to be able to navigate up and down, we will want some form of gravity. There are a lot of ways we could go about adding this, with varying degrees of complexity, but to keep things simple for the early stages, we'll just use simple linear gravity. So for now, that means no acceleration or anything fancy just yet. As we've already seen, we can use a simulation zone to move the player on an axis a set amount every frame, which is how our current planar movement system works. Using that exact same concept, we can move our player down on the z-axis to apply gravity. We can just put another vector addition node in the simulation zone, plug in our gravity vector, and there we go. So now our simple gravity is working. It moves our player down, but has no way of stopping it. Unlike Newtonian gravity, where force is being applied to you at all times, our version of gravity needs to turn on and off like a switch. We can add a switch node to our system to stop applying downward movement if it's true. But now we need something to control whether this switch is on or off. Compared to the forward, backwards, and side-to-side movement, a player's direct control over gravity is limited. With the exception of jumping, which we'll look at a bit later, our node system needs to be able to determine when to apply gravity and when not to, all on its own. Thankfully, we can add some simple rules to decide when to turn gravity on or off. Gravity should always be on unless the player is jumping or is currently touching the floor. And so now we need a way to determine if we're on the floor or not. The answer lies in the Raycast node, which is incredibly useful and is basically going to be the star of this episode. So let's spend a little bit of time getting to know it better. This node has so many applications because it can measure the distance between a point and a mesh. We can think of the Raycast like a radar system, which sends out a signal which bounces off of an object and then back, giving information on the location of objects. The Raycast is in a line, so it can only detect objects that are in its direct path. There are a few pieces of information that we'll need to give our Raycast before we can use it to detect if we're on the floor or not. There are 4 inputs we care about. The first is target geometry, which is the geometry we want to measure. So in this case, we'll just plug in the mesh of our floor. Source position is the point our Raycast will originate from. We want our Raycast to be in the same spot as our player, which we already know the position of, so we can just plug that in. Ray direction is the direction vector that we want to point our Raycast in. Since we're using the Raycast to measure the floor, we can point it straight down to 0, 0, -1. Ray length is the maximum distance our Raycast will travel before giving up and deciding there isn't anything there. In effect, this acts as our player's height because it's the length in meters the player will stay above the floor. For now, we'll just keep this at the default of 1 meter. With this information, we can now use the outputs of the Raycast. There's a lot we can do with the other outputs, but right now we only need a way to turn our gravity switch on if it touches the floor, which is exactly what the isHit output tells us. And now if we take our game for a test run, we don't keep falling through the floor. While we're on the subject of gravity, let's think about moving against gravity by jumping. And we don't need a Raycast for this, we just need another switch. So if we're jumping, we want to override gravity regardless of whether we're on the floor or not, so we'll put this switch after the gravity one. For now, our jumping will be more like a jetpack where we keep jumping until we've turned the switch off. And in a future episode, we can add a mechanism that turns the jump off automatically. And just like our gravity, we'll keep this linear for now, so no acceleration here either. Next, let's get some collision going. Basically, we want our collision to stop our player from moving in the direction that they're traveling if there's something in their way. The principle of collision is similar to gravity, but with some extra things to consider. The way our gravity works right now, the direction of our Raycast is pointed down at all times, but the collision direction needs to be dynamic and point the same direction as our player is moving. If we add all the vectors that play a part in our direction together, the end result is a single vector that represents where our player is actually moving, and it's also where we want our Raycast to be pointed. Let's pause for a second and take a closer look at vectors again. We've already used vector addition a few times so far, but it's important to understand what's happening behind the scenes. When adding vectors together, the operation will combine those vectors into a new third vector between the two. We just do basic addition to each element of the 2 vectors, adding the 2 x values together, then the y values, and finally the z. Each vector will contribute proportionally to the final vector. So if the vectors aren't normalized, meaning that they still have their length, then the longer of the 2 will affect the final vector more. Back to our collision, we'll use a separate Raycast from our gravity system since our inputs will be different. Chances are that we're going to want to have more than one thing to collide with, and using a collection info node, we can put any object we want to be able to collide with into the collection without needing to add or adjust nodes. And then that collection info node is what we'll plug into the Raycast target geometry output. And just like the gravity Raycast, we still want to use the player's position as the source position of the Raycast, so that input is the same. Our ray length can be adjusted based on our gameplay needs, and right now the main thing we'll want to keep in mind when setting this distance is the camera's focal length. We'll want to stop our player close enough to an object for it to make sense that we hit that mesh, but we also want to keep the player far enough away so that the camera doesn't clip through the wall. We plug our Raycast isHit output into a vector switch that either lets our inputs pass through if there's no collision, or just output 0 if we run into something. We add our gravity vector after the switch because we still want gravity to pull us down until we're on the floor, even if our collision Raycast has hit something. For example, if we are high up and we hit a wall, we still want it to be able to pull us down. The last functional thing I'll cover in this episode is node groups. which allow you to pack nodes together and reuse them elsewhere. It's basically the equivalent of a function in the programming world. We've added a bunch of nodes in this episode, and things are already starting to get a bit messy, but node groups are a great way to clean things up, and we can reuse those nodes over and over again without having to make everything from scratch each time. So just to clean things up for this episode, I packed the node system into a few groups, and going forward it will become a more important part of the development journey. Before we end this episode, I wanted to share a little bit about the vision I have for the Blendworks project. For a whole bunch of reasons, I don't see Blendworks as something to build commercial games with, but I do really believe that it has potential to be used in some unique and exciting projects, and I definitely have a lot of ideas for projects using it as a base. I think my ultimate goal with Blendworks is just to learn, grow, and develop my Blender skills and help others do the same while making cool things that I enjoy working on. Along those lines, I'm really hoping to get enough interest in Blendworks to host a game jam. It's still too early on in the process right now, but I'm working hard to add features and make the project as usable as possible with that goal in mind. If that's something you'd be interested in, definitely stay tuned, and if you have someone you know who would be interested in that, please send this video their way. In the coming episodes, we'll continue to add important features like traveling on slopes, moving platforms, environmental interaction, more advanced gravity, and a better way to collect user input so you don't have to use the input panel. As always, the Blender files are up on my Patreon if you want to play with the current iteration of the engine yourself, and if you have any questions, definitely let me know in the comments. I appreciate you watching my video, and I look forward to seeing you in the next one.